Hello everyone, welcome to problem 2.27 of David Griffiths Electrodynamics. So let's just jump right in. I'm a little different setup today, so bear with me. So the problem states that we want to find the potential along the axis of a uniformly charged solid cylinder, a distance z from the center. So I've drawn that situation out here. So we have a solid cylinder, and the origin is defined at the center here. The cylinder has a radius of r, and the point that we're trying to evaluate the potential at is here. And let's see, it tells us the length of the cylinder is L, its radius is r, and its charge density is rho. Use your result to calculate the electric field at this point, and assume that z is much greater than L over 2. Alright, so we to solve this problem, there's a nice way to do this. So if you recall from problem 2.25 two videos ago, part C of that problem was evaluating the electric field at a distance z away from the center of just a disk here, or actually not a disk, but like a surface charged disk, or whatever you want to call this. And so you can basically think of a cylinder as just being composed of a bunch of infinitely small disks like this, right? Just kind of stacked horizontally across the length. And so we found that the electric field, due to this situation, in problem 2.25 was given by this equation here, sigma over 2 epsilon naught, the square root of r squared plus z squared minus z. And if we think about it this way, so if you just think about one of these disks in the cylinder, then the electric field contribution due to that tiny part of the cylinder at this point z would just be the same as this. However, what we want to do is add up all of the contributions of all the disks across the cylinder. And so we sort of just do a slight change of variables here. So in our case, I'm letting the distance from the origin, I'm letting the distance, I think I labeled this incorrectly. I didn't mean to do that. Anyways, let me kind of, so I'm labeling the distance from the origin to like the variable distance here, going from the origin out anywhere as x. So in this case, the variable distance was z, and in this case, this point z here is a fixed distance. It's wherever this point is, and the variable distance I'm going to label x. So I guess that's how I had that there. And so really, in this equation, we just replace z with x. And instead of a surface charge density, we have a volume charge density of rho. And so we can just do a slight change of variables there and replace rho with that. And that will give us the contribution of a single disk. However, we need to integrate across the length of the whole cylinder each contribution from every disk. And I've kind of illustrated that change of variables here. So really what we're doing is this. The potential at that point z is rho over 2 epsilon naught instead of sigma, and we're integrating this term, which is, I just replaced z with x, and we're integrating it from z minus L over 2 to z plus L over 2. And those bounds come from this, because this length here, from the origin to here, that is z. You know, if this is L, then this is L minus L over 2, this is plus L over 2, and this fixed distance is z, so this is z minus that, so we're integrating from, and then z plus that, so z plus that, if that makes any sense. I hope it does. Alright, so let's get started. So we can break this integral out into two integrals actually. So this is going to be the same as, let me just make sure the camera can see everything. Looks like it can. So this is going to be the same as rho over 2 epsilon naught. Then I'm going to put some brackets here. And we're going to have the first integral. So z minus L over 2, z plus L over 2. And we're going to have the square root of r squared plus x squared dx. And then we're going to have minus an integral from z minus L over 2, z plus L over 2, x dx. And close the brackets. And I'm actually going to move real quick because this camera is shaking on this surface. Alright, so we got these two different integrals to solve. So let's start with the second integral since that one is the easiest one. So let's do second integral here. Just kind of label it. So we have, I'm gonna ignore the constants. We're just gonna worry about this, and I'm gonna ignore the minus sign because I can plug everything back in. So I'll have the minus sign there. So we have the integral of x dx from z minus L over 2 to z plus L over 2, and so this is just going to be x squared over 2. Evaluated from z minus L over 2 to z plus L over 2. So let's see if we can simplify some things. So we have z plus L over 2 squared divided by 2. We're gonna have a common denominator, so we're gonna do it. Then we're gonna have minus z minus L over 2 whole squared. And that should all be over 2, since they would have a common denominator. Okay, so let's, I'm wondering if we can simplify this if we expand terms. So let's try that. So on the top, we're going to have, let's see, z squared plus 2zl over 2, and then plus L squared over 4. And then here we're going to have a minus z squared. Then we'll have minus 2lz. From this we'll have minus 2zl over 2, but then the minus sign, so we'll have a plus 2zl over 2, and then minus L over 2 times minus L over 2 is positive L squared over 4. Then we have minus L squared over 4. And that's all over 2. So we end up with the z squareds cancel, the L squareds over 4 cancel, and we end up with 4z L over 2 divided by 2. So I'm just going to cancel. And so we get 2z L over 2. So that is our first integral. So we're going to keep that in mind. So that's what we're going to plug in here. And that's without the minus sign. So when we plug it in, there will be a minus. So let's move on to that second integral. Or the first integral, because that was the second integral. All right, so first integral. And I can already tell this is going to be a trig sub integral. So we have the integral from z minus L over 2 to z plus L over 2. We have the square root of r squared plus x squared dx. And then I'm going to let x, I'm going to do a trig substitution, so x is going to become r tangent of theta, I believe this would work. And I'm just going to draw a triangle out here, a right triangle. So that means tangent of theta is x over r. So if I call this angle theta, opposite over adjacent, so x, r, and then this becomes the square root of r squared plus x squared. I believe that kind of represents our triangle for our trig sub. And yeah, so plugging that in, this is probably going to end up being some kind of secant integral. So we have the square root of r squared plus, if you square x, it's r squared tangent squared of theta. So you'll have r squared plus r squared tangent squared of theta. So you can factor out r squared out of the whole thing, but then you're in a square root. So the square root of r squared is r, so you can bring r out of the integral, or out of the square root, and it's a constant. So you can bring it out of the integral, and you're just left with 1 plus tangent squared of theta, or the square root of that. And then, I forgot, dx is r secant squared of theta. So d theta, or dx becomes r. So we have another r, so I'll square that. Secant squared of theta d theta. And 1 plus tangent squared is secant squared of theta. And so we have the square root of secant squared, which is secant. So we have secant cubed here. So we have r squared times the integral of secant cubed of theta d theta. Now, there is a handy formula for doing trig integrals. So when you have like secant to the n of theta, or sine to the nth power of theta, tangent to the nth power of theta, there's these formulas that are handy when you have these nth powers of these trig functions. And so they're called reduction formulas because they essentially help reduce the power here. So the reduction formula for secant of theta, I'll write out. So reduction formula, and this is not something I just keep in my head, but whenever I do come across these, it's nice to just look these up. There's proofs for them. If you want to figure out how this reduction formula is derived, there's videos on that. You can find that. Here I'll just state it. So secant, the integral of secant to the n of theta, d theta, is equal to, so we have secant to the n minus 2 of theta times tangent of theta divided by n minus 2 plus the integral, I forgot a term here. So outside, so plus, we have a constant. We have n over n minus 2 divided by n minus 1 times the integral of secant, and subtract the power by 2 of d theta. So this is the reduction formula. So for secant to the third power, our thing will become, so we have r squared, and then I'm going to just do this. So we're going to have secant, so n is 3 in our case. So we have secant of theta times tangent of theta divided by 3 minus 2, which is 1. Right? And then plus n minus 2. So 3 minus 2 is 1 divided by 3 minus 1 is 2. So that's 1 over 2. So we have a 1/2. And then the integral of secant of theta d theta, which I always keep this integral in my head, the answer of that integral. And I've stopped writing the bounds here because I'm going to turn everything back in terms of z at the end. So, or x, or yeah, I'm going to turn everything back into Cartesian at the end. So I'm keeping things, I haven't changed the bounds yet. So we can write this out as we have r squared on out here, and then we have secant theta times tangent of theta plus 1/2. Now the integral secant of theta is the natural log of secant of theta plus tangent of theta. And close it like that. All right. So now we have the answer to our integral in terms of theta. So let's try to turn things back. So we know that tangent of theta is x over r, and that's just from our substitution, right? Secant of theta, let's try to figure out secant of theta. That's one over cosine. Right, so secant is just 1 over cosine. And cosine of theta is adjacent over hypotenuse. So cosine is r over this. So secant would be that over r. So it'd be the square root of r squared plus x squared over r. So that's secant of theta. And that's all we need to plug everything in. So let's turn everything, and I'm just going to write this. So this is evaluated from z is minus L over 2 to z plus L over 2, but I haven't turned anything back into z yet, which we're about to do on the next page. So let's do that. So we're going to have r squared, and then so secant of theta is, so we have the square root of r squared plus x squared, and then times x. So tangent of theta is x over r, so times x, and this is over r. And then plus, we have a 1/2, a natural log of secant of theta, so we have the natural log of the square root of r squared plus x squared over r plus x over r. So now we've turned our theta answers in terms of Cartesian, so x, and then this is going to be evaluated from z minus L over 2 to z plus L over 2. All right, so now we can start doing this. We can start doing this bound evaluation, which is going to be quite a lot of algebra, but we'll get through it. So r squared. Let's see. So we're going to plug in this for x. So we have the square root of r squared plus L squared over 4. And then z plus L over 2 all over r plus 1/2 the natural log of the square root of r squared plus L squared over 4. Or, no, not L squared over 4. What am I doing? It's z plus L over 2. So, I've messed this up already. Let's start over. That's what I get for doing this live, is I make mistakes. So r squared plus z plus L over 2 squared. And then times z plus L over 2 all over r plus 1/2 natural log square root of r squared plus z plus L over 2 squared over r plus z plus L over 2 over r. So I can really put these into one term here. Okay. So this r squared is, this is like a constant outside of all this. So I can keep the brackets open and now do the other bound. And so we have a minus sign. And I might just distribute the minus sign through. So we have minus the square root of r squared plus z minus L over 2 squared, right? We have z minus L over 2 all over r. We have a minus 1/2 the natural log of, and we know this is going to be r on the bottom, so just put r. We have the square root of r squared plus z minus L over 2 squared, and then let's see, minus, so minus z minus L over 2, or not squared, just that. That's the natural log, and then I can finally close the brackets. All right, so this is what I have for the bounds. The real question is, how can we simplify this? I'm taking a look at some of my notes from when I previously tried to do this, but I did them wrong initially. So when you have natural logs, like a positive natural log here minus a natural log, so that can be combined into a single natural logarithm. So we can probably do that. We seem to have a common factor of, well, no, because that r is, well, let's just see. Let's combine the natural logarithm first. So we still have our r squared out here, and we're going to have this first term. So, and I'm not sure if I want to expand stuff in here or not. So if I did that, that would be z squared plus 2zr L over 2 plus L squared over 4, and then plus r squared, which I'm not really sure if that really does anything. I'm not, r squared, plus, I'll just keep it in, and we have z plus L over 2 here, all over r. My question is, I wonder if these two terms, so that's going to be z squared minus 2zl over 2 plus, like these two terms both have a denominator of r. We're going to work with this next. Let's worry about the natural logarithm first. But what I'm going to do is put this term after this one. So we're going to have minus, I'm going to get the natural logarithm term last, plus z minus L over 2 squared times so we can combine these two terms into one long term. I'm wondering if we'll be able to do something with that. Okay, so that's this term minus this term, and then let's figure out how we're going to do this. So we have plus 1/2 natural logarithm of this. We have minus 1/2 natural logarithm of this. So we can factor out a factor of 1/2. So I'm going to go to the next line. So we're going to have, let's just say plus 1/2, or yeah, I don't know, plus 1/2, and let's do a open bracket like that. And so we're going to have the natural log, so we're going to have positive natural logarithm of this minus the natural logarithm of this. So that's going to make it a natural logarithm of this divided by this, and this is all over r, this is all over r, so those two r's are going to cancel each other, so we're going to have just the top terms. So we're going to have the natural logarithm of, we have r squared plus z plus L over 2 squared, and then plus z plus L over 2 divided by the square root of plus z minus L over 2 whole squared. I think there should be a, oh wait, what am I doing? No, I'm good. And then this is minus z plus L over 2. Really? If I distribute that minus sign through? I don't know. I could get rid of the brackets here, right? So that's the natural logarithm term. And then kind of like that. So we at least simplified this term to some degree. This is still an ugly argument, but I don't know how much better we can really get. Now let's combine the top. I'm trying to think. So here we have a common denominator of r, which means we can write this as one big fraction. And this times this is going to be z squared plus zl over 2, or minus zl over 2 plus z over 2, so the middle terms cancel, and then a minus L squared over 4. So, I mean, it doesn't really do much, to be honest. And then here, we have these two square root terms. Although, yeah, I mean, I'm just gonna have to leave it. Unless I can figure out a way as I go. I'm gonna rewrite this, and what we're gonna have, because eventually we need to plug this back into the integral. So we're gonna have the square root of r squared plus z plus L over 2 whole squared times z plus L over 2 minus the square root of r squared plus z minus L over 2 squared times z minus L over 2, right? And this is all over r. And then I don't have enough room, so I'm going to have to write the second term down here, and then plus we have 1/2 the natural log of this nasty stuff, r squared plus z minus L over 2 squared plus z plus L over 2 divided by the square root of r squared plus z, sorry, this should have been plus up here. This is minus z minus L over 2 squared minus z plus L over 2. And that's about as simple as I can really get it, I think. I don't know any other way to get this simpler. I mean, just looking at it. I'm sure, I mean, you could expand everything in there, but like, why make it even more? It doesn't help me cancel anything. Yeah, if you guys see a better way of simplifying this, let me know. But I'm going to keep it in this form for now. So I'm going to plug everything back in. So if you remember, way back here, we started out with this integral. And we solved this one, which gave us this. And we just finished solving this one, which gave us this bad boy. So we're going to plug everything in now. So V of z, so we have the rho over 2 epsilon naught. Rho over 2 epsilon naught times, so the first integral is this. So we have the we have the r squared term, I guess. I forgot to well, let's you know, if we I guess I could get rid of this fraction on the bottom here if I just distribute that r squared in. We'll just have r on top. But I don't know. It's really not a huge deal. Here, I'm going to rewrite this. Sorry, guys. I'm going to rewrite this. So v of z. So we have rho over 2 epsilon naught on the complete outside. If I do distribute that r through, then what we have is, you know, that cancels that. Well, not exactly, because this r distributes over both these terms. So this r cancels with that one, but we still have r squared here. So that's not very accurate. I shouldn't have crossed that out completely. But here we have r times the square root of r squared plus z plus L over 2 squared times z plus L over 2 minus the square root of r squared plus z minus L over 2 squared times z minus L over 2, and then that, because we still have the r, and then plus r squared over 2 here, because I distribute the r squared through, and the natural log of all this stuff which is just nasty, but it is what it is. Nothing says nature has to be nice. And then minus the, so that's the natural logarithm term. And then plus the second integral, which was very easy. It was just like plus 2z L over 2, which was the second integral. And closing all that out. So, I mean, this is what I'm gonna leave it as. I mean, there's probably a cleaner way to write this. But if you saw any mistakes that I made, please let me know. I'm gonna quickly double check that to see if this sort of matches what some of the other solutions I've seen are. So, but if so, we will move on to finding the electric field from this potential, which is actually going to be nuts. So, yeah. Okay, so after checking with the book, some solutions I found, this does appear to be the right answer, and I forgot. This should be a minus sign here. Remember from the integral, I had mentioned this. It's it's this integral minus this integral. So when I plugged in the solution, I forgot the minus sign. So this is minus 2zl over 2. But this does appear to be a correct solution. So if I could have missed something, I just let me know. I'm trying to just make sure that I did not, but I very well could have. I could be off by a factor of a half or something. I don't know. But if you guys, I did double check and it did look pretty much exactly like what I had. So, yeah, so we're going to move on now to the electric field part of the problem. Okay, so I decided after working on this for a bit, I actually did start trying to derive the electric field by hand, and I went through several pages just to. I ended up getting a solution, but it wasn't exactly right. I did make some mistakes. The derivatives are quite nasty. You got many chain rules within quotient rules and product rules and all kinds, and there's lots of places you can easily make a mistake. And so I made this mathematical file, and I've just defined some constants here to make the equations easier. And this is the electric potential function that we found in the previous part, just written in Mathematica. And all I've done is to calculate the electric field, I took the negative 1 times the derivative of the potential with respect to z, which would give you the electric field. And so that function is outputted here. We have rho over 4 epsilon naught, and then big bracket and all this kind of stuff. So you can see how awful this is. And let me see if I can zoom in. Window magnification. Here we go. So yeah, you can kind of see better how awful this would be to calculate by hand. So I ended up getting something fairly close to this, not gonna lie, but I just thought it would be worth to, or much easier to just plug this into Mathematica and let it take care of it. I will throw this Mathematica file as well as a PNG image that you guys can download and take a look at if you guys want. The derivatives themselves aren't that hard necessarily. There's just a lot to keep track of. So it's a lot to handle. And I decided to also graph. So what I did was define some constants. So I defined like the radius and the length of the cylinder, the charge density, and this is just the permittivity of free space. And all I did was plot, so that way the function only depended on z, everything else is fixed. And I plotted the potential as a function of z on just a range along the x-axis, so you can kind of see how the potential changes. So the length of the cylinder in this case was 10, so from negative 10 to 10 is where that the ends of the cylinder are, and then outside of that. So you can kind of see how the potential function changes over space here. So I hope that's helpful. But yeah, I didn't really have steps for this, but I will provide you guys a Mathematica file as well as an image to this file here. And yeah, I think that will be the most efficient way to do this, because otherwise this video would have ended up being like over an hour long of me just trying to work through a bunch of math, and I think that's not as helpful. But who knows? Maybe you guys would like that. So I don't know. You guys let me know what you guys like. So I hope this is helpful. You guys can find these files in the description, as well as my Patreon. I do have a Patreon account now, so if you guys do want to support the channel, you can go over there and subscribe. I have a remarkable ink tablet coming in the mail next week, and once I get that, I'm going to be doing my videos solely on that ink tablet. And what's cool is I can take my solutions directly from there, upload them as a PDF to my computer, and I'm going to have a private Google Drive for my Patreons subscribers to access that private Google Drive, and you guys have access to all the PDF solutions to my videos. So once I get that tablet, I will start creating PDF solutions for my videos, and my Patreons will have access to those. And there's another tier as well on my Patreon that you can take a look at. So thank you guys for watching, and I hope you guys have a fantastic day.